In the last video, we introduced spin, and we wrote down our spin eigenfunctions in terms of s squared and the basis set for s sub z. We now want to talk about spin in an alternate basis. In this particular case, we're going to talk about the what spin looks like in s sub x. We're going to start with the eigenvalues and eigenvectors of s sub x. We'll then talk about the generic spin matrix or spin state in the s sub x basis. And finally, we'll talk about sequential spin measurements. So let's ask ourselves a question. What are we going to observe when we measure s sub x? Well, by a symmetry argument, in principle, without any other defining features in Cartesian coordinates, the sx axis should be the same as the sz axis or the sy axis. So we might expect to get the same eigenvalues. So let's see if that actually is the case. We'll start with an eigenvalue equation for s sub x. S sub x chi is equal to lambda chi. Now, the matrix, the matrix for s sub x, remember, is h bar over 2 times 1 in the off diagonals. So if we rewrite this eigenvalue equation and take it, the determinant setting it to 0, it's the determinant of a matrix, a 2 by 2 matrix, which is minus lambda, h bar over 2 minus lambda. Well, that gives us 0 is equal to lambda squared from this term minus h bar squared, h bar over 2 quantity squared. Clearly, this means that lambda is equal to plus or minus h bar over 2. So in fact, the eigenvalues of s sub x are the same as the eigenvalues of s sub z, which makes perfect sense because of symmetry. The eigenvectors can be obtained by assuming an arbitrary spinor, alpha beta. Now remember, this is in terms of the spin up and spin down in the s sub z basis, the one we've defined up to now. We're now asking ourselves, what are these vectors going to look like in the for s sub x? What are the eigenvectors for s sub x in terms of the spinor up and spinor down vectors? Well, we can write that matrix equation as h bar over 2 times the matrix 0, 1, 1, 0. Then we have alpha beta is equal to plus or minus h bar over 2 alpha beta. Clearly, we take the h bar over 2's cancel, and so we have beta for the first term at the top and alpha for the term at the bottom. And on the other side, we have plus or minus alpha beta. Well, this tells us that beta is equal to plus or minus alpha, or alpha is equal to plus or minus beta. There's redundancy there. We only need one of those. So beta is equal to plus or minus alpha. That means that for spin up in the s sub x, the spin up for s sub x state, we are going to label it as chi plus in the x basis, with the x up here, means we have the positive sign here. So we have 1 times over the square root of 2 for normalization times 1, 1. And the spin down is the minus sign here. So we get chi minus in the x basis is equal to, in the x direction, is 1 over the square root of 2, 1 minus 1. Now the 1 over the square root of 2 is there because we have to have this normalized. When we have 1 and 1 here, we take 1 squared plus 1 squared gives us 2. This squared gives us 1/2, and the whole thing is normalized. Same with this. So how's a generic spin state, the AB, represented in a basis of eigenfunctions of s sub x? Remember, we had our generic spin state, a vector AB. We can rewrite this in terms of the s sub x eigenfunctions, chi plus x and chi minus x. And we have two new factors, c and d. Well, again, This is straightforward because we know what these are in terms of vectors. So this is c times 1 over the square root of 2, 1, 1, plus d times 1 over the square root of 2, 1, minus 1. This results in, and this is equal to the vector AB. So we can write this down very simply, that A is just the sum of the top two elements here, which is 1 over the square root of 2 times c plus d, which is this. Similarly, B, which is the lower element, is 1 over the square root of 2 times c minus d. And that I have over here. I can now proceed to solve for c and d in terms of A and B. So the first thing I want to do is solve for c here. If I do a little bit of rearranging and multiply times square root of 2, and I bring the d over to this side, I have c is equal to square root of 2a minus d. I now can substitute that value of c into here, and I get 1 over the square root of 2 times the square root of 2a minus d. So this is minus 2d. And then if I divide through by the square root of 1 over the square root of 2, or the square root of 2, I have a minus the square root of 2d. Or d is equal to a minus b over square root of 2. Just rearranging this because this is equal to b. And so I can bring the a over to the other side, or the b over to this side, and the square root of 2d over the other side, and I get a minus b over square root of 2. If I then take this value and put it back into here, I get, for c is equal to square root of 2a minus 1 over the square root of 2a minus b. And this simplifies to c is equal to a plus b over the square root of 2. So c is equal to a plus b over the square root of 2. D is equal to a minus b over the square root of 2. And I can write my generic spinner, which in terms of the S sub z basis set is equal to AB. In terms of the eigenfunctions of S sub x, can be written as a plus b over square root of 2 times chi plus x, plus a minus b over the square root of 2 times chi minus x. The probability of measuring the two possible eigenvalues for S of x, that is h bar over 2 plus or minus, is therefore given by just the square of each of these coefficients, because these are normalized. So px plus would be this term here, which is a plus b over the square root of 2 modulus squared. A and b could be complex, which is the modulus squared of a plus b divided by 2. Similarly, px minus is equal to a minus b over the square root of 2 modulus squared, or the modulus squared of a minus b divided by 2. Now, what if we want to do some measurements? Let's imagine that we start with an electron in the chi plus state. Now remember, the chi plus state is the spin-up state in the S sub z basis. And then we measure the expectation value of S sub z with this. We'll get the following probabilities. If we know that we prepared it in the chi plus state, when we measure S sub z, we get pz plus is equal to 1, and pz minus is equal to 0, because it's in the plus, the spin-up state. And that's pretty straightforward. What about if we measure the expectation value of S sub x? We get the same two eigenvalues, but the probabilities are different. The probability that we measure px plus is 0.5. It's half. The probability that we measure px minus is also 1/2, 0.5 rather. And the reason is, remember that the basis vectors of these are different than the basis vector for chi plus. So chi plus is really just a linear combination of the eigenvectors of S sub x in such a way that all that remains is the chi plus vector. If we then have measured that first result, that is, we measure Sx as plus h bar over 2, then if we measure Sx again, and continually, as many times as we want to measure it in a row, we'll always get px plus equal to 1 and px minus equal to 0, because we know it's in the state of plus h bar over 2. When we then want to measure S sub z, will give us back the probabilities of half and half again. Because now the system is in a state, the eigenstate of S sub x with eigenvalue plus h bar over 2, but that's not an eigenstate of S sub z because S sub z and x sub x do not commute. Right? Since they don't commute, it's not possible to know both their values at the same time. You either know one and you don't know the other, or you know the other and you don't know the first. So what this means is that when you make a measurement of S sub x is made and you know its value, the value of S sub z is lost. It's now randomized. It's half and half. You don't really know what it is anymore. So this is just a consequence of the uncertainty principle and the fact that we're using the Copenhagen interpretation, or the Copenhagen interpretation, that is the probabilistic interpretation of quantum mechanics. This is probably one of the harder concepts to realize, is that it's sometimes called a wave function collapse, that when you measure S sub x, you will get a value, and then you change the system, so now you get a different measurement when you go back and measure S sub z.